In the previous video clip, we have seen a brief definition of model selection scores and see how they can be applied to select model order in some examples. In examples of choosing autoregressive lag order, in using choosing the polynomial order. So in this video clip, I would like to go over the properties of these model selection scores, go over the motivation and mathematical description in a little bit detail. Okay. Probably I should show this slide again. Okay, so we have seen model selection scores. The first three of them are the one that are based on the log likelihood function, AICc, corrected AICc and Bayesian. All right, AIC, AICc, BIC. Oh, and also closely related is final prediction error criterion. And the last two ones are model selection indicators that typically derived in the context of linear regression. So we start with the first three ones. You see that AIC, AICc, and BIC consider a trade-off between model quality and model complexities in additive term like this. The model quality is is explained by the negative log likelihood function. And recall again that in order to obtain the log likelihood function, it means that you must have assumption of data generating process, and also about the whatever your model, whatever the data generating process is, if there's some random variable, some random entity that basically typically is noise term, you need to have some assumption about the noise distribution in order to derive the log likelihood function. The second part of this score actually accounts for model complexity. Let me recall again. The term that represents model complexity is D. D is effective number of parameters. Okay, so we go over this. You can see here that basically the term that is multiplied with D, these are different in each score. For AIC, there's a factor 2. For AICc, of course, there's the additional term, okay, in addition to the AIC score. And for BIC, the constant that multiply to D complexity is actually logged in. Okay. For AIC, this is some detail in when deriving the AIC. This is actually AICc is the name of a statistician who proposed this score. In statistics, there's a measure function. Sorry, there's a distance function. It's called Kullback-Leibler divergence. This is notation given by I, F, and G. Basically, you have distribution, two distributions, F and G. Typically, F is used to refer to a true model, the true density, and distribution G is used for model, your assumed model. For example, the random variables have Gaussian distribution, right? With the true density mu and sigma square. This is the true parameter. And in your assumed model, you may be like you assume to have something else. That is possible as well. For example, you may assume that, oh, my distribution is Laplacian. Okay. So KL divergence is a metric. You can think of this as a metric. Is is a function, is a distance function that require two inputs, which means a two density function, and it returns a scalar. All right. This scalar just tells you how the density G is far away from the true density, and its description is given by this this formulation. Obviously, when we take a look at this, KL divergence. If you have, of course, if you have samples draw from the true density from F, right? This is density, which means this is a probability density function. Okay, and of course, G is the assumed density. Obviously, Fx must be bigger than Gx, right? If you evaluate at some samples or some samples that draw from the population, the true density must give the higher value because it's the true distribution. Okay, it gives a higher likelihood, which means this quantity is always bigger than 1. When the log is bigger than 1, this guy, the true density F, is non-negative, right? So the KL divergence is always a non-negative value. And of course, the higher the value, it means that the further away of G from F. Okay, so if you assume the model correctly, okay, the smaller value of KL divergence you will get. Okay, so that's something from statistical point of view. KL divergence is also used a lot in communication, in other fields as well. All right, so what it has to do with the AIC score? Okay, so when you have a zoom model GX theta hat, right? Theta hat is the value of model parameter you estimated. AIC score is derived, which is derived by AIC, is derived in such a way that the negative log likelihood plus D, all right, plus D, is an approximation of the average of KL divergence, is the average overall theta hat, overall model's parameter, okay, plus some constant. So which means that we'll use the term that the AIC, okay, is an approximate, but it is a biased version of the expectation of KL divergence. All right. So which mean when you minimize the AIC, the meaning is you're trying to minimize the average distance of two distribution. Actually, we have to say you're actually minimizing the average distance of the model you consider, right? The distance of the model you consider to the true distribution, to the true model. Okay. So that's the explanation of AIC. For AICc, you will see that there's an additional term here in the green box, all right? And which means this green box also a function of D that represent the model complexity. And when n is small, all right, when n is small, this can represent the finite samples scenario. Of course, when the denominator is small, you have numerator as a quadratic function in D, which means this term is going to give more penalty on the model complexity. So which means that in the finite, in the small sample scenario, it will be clear that between AIC and AICc, the AICc will prefer a simpler model in comparison to AIC. But when the n is getting large, in the scenario that when n is it's very large, a lot of the samples are available, these terms approach 0. So the behavior of AICc will also approach the AIC. And the last one in this category, the Bayesian information criterion, or BIC. Okay, so compare between BIC and AIC. As I pointed out, that the factor or the constant that multiply with d for AIC is 2, for BIC is log n. Okay, and of course the coefficient that multiply with d, the higher value means the more penalty you put on the model complexity. So if you compare these two factors, log n and 2, okay, obviously these n typically represent the number of samples. So this guy we can say that in practice, of course, this log n is going to be bigger than 2. All right, and that basically means the AIC would prefer a simpler model again compared to AIC. All right, we also see this from previously on the experimental result when we see the graph, right? For example, for BIC here, it picks the model order 2. For AIC, which is the red line, it typically picks a more complex model. Okay. The BIC has a nice property about asymptotic behavior. It says in the original paper of Bayesian information criterion that suppose you have a candidate, a set of candidate models, and suppose that the true model is one of them. The true model is one of the, one in the catalog for you to choose. It can be shown that if you have a lot of sample size, you have a lot of samples when n approach infinity, the chance that you will correct, the chance that you, after you apply BIC, the chance that the BIC chooses the correct model is approaching 1. So with this description, we use the term consistency. So the BIC as a model selection score has a consistent property. Okay, but I mean this assumption is important. All right, this result is obtained under the assumption that the true model must be one of the choices. The BIC also has a lot, has another important meaning in related to Bayes theorem. Okay, so in short, we will see that the model that is selected by BIC, which means the model that selected with the minimum BIC, is actually the model with the highest posterior density. So now let's take a look at this term. Suppose you have two models. You have M. Suppose I use this subscript. Like M is a model. Subscript M is just just the name, just the index. All right. All right. Take a look at this this quotient. This is the probability of model. The probability of the model, which means that basically it's the same as the likelihood, right? The probability of the log likelihood of these of this model, given that, all right, this is a conditional probability, given that you have observed these data. So this data means that you're gonna given the value y1, the dot yn that you collect from the measurements. All right. So when you compute the probability, the conditional probability of model M, all right, divided by model L, this ratio, this is called odds, the odds, all right. And we put some prefix here, posterior odds, to emphasize that this is the odds after we observe, after we use the data point. Okay. So I mean this guy, all right. Each term, this is the posterior density because again this is the probability of the model after you observe the model. Oh, sorry, after you observe the data point. All right. When you see these posterior odds, all right. Okay, how can you choose? Suppose I give you this the value. Suppose somehow I can calculate the value of posterior odds. So if it turns out to be 0.8, okay, what does it mean to you? Which model should I pick? Model M or model L? Top.
Yes, Ajahn.
Yes.
0.8 model L.
Because
It has higher probability.
right. Okay. If these the posterior odds turn out to be 1.2, which model do you pick?
Model M.
Model M, right? Okay. So this is of course this is a simple way to look at it. And now this posterior odd, if we use the Bayes theorem, okay, which means like everyone know that probability of A given B if is what is A B, right, and divided by PB, okay, and then the Bayes theorem, the Bayes rule is actually a way just to write this in another form, which is ping. Right. All right. Okay. I just that's I just presented. So this is a Bayes rule, right? Conditional probability A given B can be rewritten again as, you know, probability of B given A and so on. So which means the posterior odds, right? After you apply this Bayes rule, can be written as the product of these two terms. The terms in the pink box is called a prior density, because this is the ratio of probability of model M to model L. Right. So what does it tell you in this prior density? Which means suppose which means if somehow I have if the probability of model M is 0.5, let me say, okay, suppose you have M1, all right, and model M is one of them, model L is one of them, all right, and suppose you have 10 models. If I have probability as 0.5, I have ML as 0.1. Okay, so what does it mean in practice? It means that you have some background information about these two choices. Like you have your own preference without observing any data or anything. You already have like you already have a preference choice that model M has a higher chance to be picked than the model L. All right, this is also possible in practice to come up with the prior density. For example, but it typically done from knowledge in a particular application. For example, think about probably model MM is this, right? Model ML is like think about like the simple case linear regression. model MM, all right? Suppose you do the regression, you can think of biomedical application as well, total, like you do the variance, right? Variance and arousal estimation, okay? Model MM, suppose it includes, what do you pick as a feature again, total? Can you get put some example?
Too many feature. One of this is the scaleogram, Achan.
Okay, I'm gonna say that basically that represents energy. Okay, let's say it is energy in band 1, all right, the frequency band 1. Okay, can we put it in this way? And of course, this is band 1. Can you make an example about another features?
Energy in band 2.
Okay, energy in band 2, all right. All right, suppose, of course, model M is has 2 features, model L has 1 feature. Suppose in your application from your domain, your knowledge, like you're the expert in this field, like you already know that the emotion, I don't know, this is something I make it up, all right? If you know that the emotion that aroused by, activities in the brain is activated in two frequency bands. Somehow you already knew that, right? Which means you believe that, of course, including the second features is crucial. It must be done, all right? Which means in this case, whatever estimation method you pick, all right, which means with this scenario you can say that, oh, I have a prior density that model model M that contains 2 features, and these 2 features are really important, right? These are essential features. So then with this, as a user, you can put a prior density, a prior probability of model M to be bigger than model L. All right. So so the term in the pink box is typically assume or kind of it actually came up from users from this knowledge. All right. So it can the term in the pink box is one of the factor to calculate the posterior odds. All right. Now let's take a look at the yellow box. The yellow box is actually the probability of data given the model. It's actually this is a term. Sorry, this is the actually log likelihood function that we derive in the ML scenario, right? Probability of data y1 dot yn, given that you use the model parameters, you use the model structure according to model M. Okay, so so probably when, sorry, let me go back again. I think when I explain the term in the green box, I think when I say this is the log likelihood, so I shouldn't have said it, all right? I should have stick to the term that this is posterior density, sorry, okay? The log likelihood term should be refer to this one, right? Okay, now when you see the relation of this guy, all right, so in conclusion, the green, which is posterior odds, if you know this quantity, it will allow you to choose a model, right? It allows you to choose the preference between model M and model L. Now let me go back to this case where what, probably in some of the in some of the applications, if you don't have any preference, if you don't have any information about the prior density, all right, for example, like one, I'm not in biomedical, right? I have no knowledge, like background knowledge about the brain signals and everything. So the obvious choice of me, the obvious choice, you know, from me to assume the prior is, okay, maybe I assume the uniform. Like all the models have equal chances, right? That's seems to be the, like the most common one that user would pick. In that case, all right, so in that case, this is 1, right, the ratio. And you see that the term that will have the highest influence to the posterior odd would be the term in the yellow box. And the term in the yellow box is called the Bayes factor. All right, the Bayes factor. Okay. Here's the connection with the Bayesian information, with the Bayesian information criterion. The Bayes factor, okay. This is some derivation in the Hasty books. AIC score, all right, and when after you account for the -2 factor, the AIC score is actually an approximate of the Bayes factor. Okay, so that is why but with the -2 factor, it means that you have to flip the sign, flip the meaning a little bit, which means the model with the minimum BIC, all right, will relate to the highest posterior odds, you know, through the Bayes factor, because BIC is an approximation of the yellow box, probably with the flip sign as well. Okay. Okay. So that's the meaning. All right. Now let's compare each model selection score a little bit. All right. Suppose I have two scenarios. I have one scenario. I have a complex model, and I have a simple model. All right. These models are nested. Model M1, which is more complex, but model M2, which is simple, is nested in model 1. For example, my model M1 could be like, it has, okay, let me put it in this way. My model M2 has n features, all right, and my model M1 has m more features, which means it has xn bn plus xn plus 1 beta n plus 1, go all the way up to n plus m, beta n plus m. So my model M2, we call it nested because you can think of model M2 as a special case of M1. It's a special case when the coefficient, the green beta are all 0 in model M2. Okay. In this case, we can kind of model it in the way that, okay, D1 is D2 plus M, right? Okay, now let's take a look at the AIC score. It's -2L, right, plus 2D. Okay, which means now I'm going to compare these two models, compare the scores. Okay, AIC1 is going to be -2L1 plus 2D1. AIC2 is going to be -2L2 plus 2D2. All right, but D2 in this example, I make the model 2 such that D2 is what? Is bigger than D1. Oh, it's the other way around, sorry. Model M1 is the complex one, right? Okay. Okay, everyone okay with this? All right, model 1, model 1, like D1 is D2 plus M, right? That's how I end up here. Okay. So if now ping, okay, if AIC picks the complex model, which means between AIC1 and AIC2, which one is smaller?
The AIC2.
Hmm?
AIC2 is smaller.
Model M1 is a complex one. Model M2 is a simple one.
Yes.
If AIC pick a complex model, can you compare these quantities?
Or AIC1 is smaller than AIC2.
Model AIC1 is going to be smaller than AIC2, right? So you just compare. Okay, so now we have this relation, and from this relation you will see that AIC will pick a complex model when the log likelihood from model M1, of course, is bigger than the log likelihood model M2 by a threshold of 2m, which means the improvement you gain in the log likelihood function is big enough that you can, I think it's worth like trading off with the model complexity, increase by the values of m. All right, now let's take a look. So if you do the same way for BIC to pick a complex model, it's going to be worthwhile picking the complex model if the gap or the improvement you gain from log likelihood exceeds the threshold of m times log L. Okay, so if you think of this as the threshold to be obtained in order for score to select a complex model, which means if this threshold, okay, this is the gap, right, the the delta log likelihood, like you think as this as the threshold. If the threshold is small, which means if a threshold of some model selection score is small, it means that it's easier for that score, right, to pick up a complex model, right? Like for example, if a threshold is 1, for example, oh, I just need to improve the log likelihood by a values of 1, and then my score will have a preference on the complex model. In another scenario, if the threshold is 1000, oh, my model, if I need to invest on using a complex model, the complex model must improve the model quality by this big threshold, by 1000. All right, we can use it this way to compare, which means when we compare between the threshold of 2m from AIC and the threshold of m log n by BIC, which values are supposed to be bigger total between 2m and m log m?
In practice, it's bigger m log n.
M log n is, of course, typically bigger than 2m, right? It means that AIC only require a threshold of 2m, smaller values, so it's going to be easier for AIC to prefer a complex model. Or in other words, in an equivalent way of saying that, it means that for BIC will prefer a simpler model. All right, and that's again that confirm everything we see from experimental results here. Okay. We have all right, I have some explanation about the log likelihood ratio test as well, but since we haven't learned about this test, but maybe I can explain in short that in the log likelihood ratio test, which is one of the hypothetical tests, all right, it basically says that the log likelihood ratio, all right, has asymptotically a chi-square distribution, where the m is the difference of model complexity between the model M1 and M2. Okay, so in this log likelihood ratio test, if if this quantity we call is test statistic, if the test statistic is bigger than the critical value obtained from the chi-square distribution, all right, you will reject the null hypothesis, and then the null hypothesis is that you assume a simpler model. So like in short, if you perform the log likelihood ratio test, the test will end up choosing the complex model if this gap, if the log likelihood of model M1 is bigger than the model M2 by a threshold of critical value. Okay, and this critical value, all right, this is something that you need to look it up, right? You can compute from the inverse cumulative density function. User put significance level, typically 0.01, 0.1, 0.05, all right. Now again, it's the same scenario as we discussed from with AIC. All right, if the delta L exceeds this critical value, the log likelihood ratio test will pick a complex model. So when you compare the threshold, you know, from the log likelihood ratio test, you compare it with 2M from AIC. You will see that, of course, these values depends on M, but for when M is around like less than 7, this 2M is less than the critical value. Again, when the threshold is smaller, it means that it's easier for AIC to pick a complex model than using the log likelihood ratio test in this case. Okay. All right. Now next I would like to explain about the final prediction, AICc final prediction, or FPE. As we see before, the terms V is the loss function in the PEM method. All right, and this term, the lower, it means that the better model, the better quality of the model. In this FPE, as I said before, the trade-off between model quality and the model complexity is represented in multiplicative form. All right. So for a simple model, the values in the loss function would be Ping. Can you answer that? When you have a simple model, the loss function is big or small?
Log function, right?
Loss.
Small again.
Simple model.
Big again. Sorry. It have big.
It's big, right? So okay, for a simple model, of course, the complexity is small, right? When the complexity is small, the ratio of this guy is small. Of course, this is, you subtract it from 1 as a denominator, like the whole thing. Sorry, not. So this term, if you plot, I mean, actually you need to plot this. You need to plot this function as a function of d, all right? When d is small, this term is small, but the loss function is big. So on the other hand, when you have complex model, the loss function is small, but the yellow term is bigger. Again, you see a trade-off, right? You need to find a good balance, the optimal balance between these two guys. Can we recall the loss function we use in PEM? So in PEM, remember that we have prediction error, right? And then this could be vector. And then we have compute the sample covariance of the error, which means we compute this outer product of prediction error. And then this is our matrix, all right? It depends on the dimension of y. If y is a vector, of course, we have this transpose thing. And of course, the loss function, when we'll see the lecture of PM, they can have many choices. Depends on the loss function you pick. Some of the common choice is the trace function or the dead function, as we see before. These things are simplified when the model has scalar output. When this becomes scalar, this guy is a scalar 1 by 1, okay? So R, the covariance metric here becomes total. The prediction error is a scalar. It becomes total.
Error square.
Error square, right? Error square. And of course, this is all the scalar. If you plug it back here in the loss function, what is the trace of R when R is a scalar?
Just the original value is a square.
Yes. So that's why when the model output is scalar, okay, everything simplified, all right? And the meaning of this is basically the sum square divided by n. That is basically MSE, right? The term. So if the expression of FPE is simplified to this case when the model output is scalar. The meaning of CUEE final prediction error is that in the Lung book, this is the system identification textbook. So this score is a way to approximate the limit of expected value of the loss function. This is the population mean, ensemble mean in the large sample scenario. Okay, in the book it says that FPE is approximate version of this. Okay, and can be it is the estimated version when you use V, the loss function of theta hat that evaluate on the estimation set. Okay. Next, the next two scores are actually, as I said, are typically applied and used in the linear regression model. The Mallows CP coefficient, okay, is used in linear regression. D is the number of predictors you use in the model, and the score is represented under the assumption that the noise corrupted in the DGP data generating process, this noise is homoscedastic. All right. So each EI, the variance of each EI is assumed to be constant. I mean, they are all equal noise variance. Okay, the score again consists of two terms, the model complexity and the model complexity. But with a little detail here that the sigma hat square using the CP, it is an approximate of noise variance using the full model, which means suppose your full model has 10 features, 10 predictors, right? You use all those 10 predictors in the linear regression. You compute the residual, all right? Compute the residual and compute what the way to calculate sigma hat square. Sigma hat square is 1 over n minus all the number of predictors in the full model, and this is the norm square. Okay. Which means when you evaluate CP, as you vary the model complexity, this sigma hat square is the constant term obtained from the full model. And of course, for simple model, repeating again, for simple model, RSS is small or large?
For simple model, ORS should be large.
Should be large, okay. The model complexity, the term D should be small or large?
Small.
Okay, right. So when you have complex model, of course RSS would be smaller, but the term D would be bigger again. RSS is always decreasing, right? In Hasty book, again, the meaning of CP is an approximate, again, is approximate of the test MSE. This is MSE on the test data set, right? If you see another textbook, another document, you might see that another expression of CP is available. It also represented this way, as if you kind of divide it by sigma hat square, the whole term. Other form exists, but I mean, if you choose this CP in choosing the model order, if you end up choosing the same model complexity. The last one, adjusted R square, has again has been used in linear regression context. Originally, R square is derived, only the R square is derived under the decomposition that of course, now we take a look. Y is the response variable. Y bar is actually the average of yi, right? So the meaning of Y bar is actually it basically represents our prediction from the simplest model, and that model is the constant model basically. All right. Because if you can recall, if I wanna run a regression using a constant, I don't use any predictors at all, just a constant. You will know that in a linear regression, your intercept term hat estimate is actually Y bar. That's a math result. So here in the TSS total sum square, it basically see how you can use the simple model, the constant model, right? And so this is the error of the constant model. From algebra, you can prove that this equation holds, this identity holds. So the first term on the right hand side is actually the residual sum square. So this is again the error obtained from your model, a particular regression model using a certain number of number of features, right? And of course, CSS, ESS, this is the term to say deviation between your regression model of interest and the constant model, all right? And we see we have the crossing term, okay? So in the linear regression, it can be proved that if your model contains the constant term beta 0, this term is 0. The crossing term is always 0. So that's why these equations hold. TSS equal RSS plus ESS. Okay, and the R square is defined. So if you basically divided the whole thing by TSS, all right, you will get 1 equal RSS more ESS. Okay. So R square is defined as 1 minus this, which is this term, all right? And you will see that the R square, okay, the R square, the higher the better. The higher the better, and its approaches, it always bigger than 0 and less than 1, okay? Now, because R square doesn't take account for the model complexity at all right? So in the definition of adjusted R square, it has the term that compensate the model complexity through D here. So as we see before, So when you have a simple model, d is small, right? When d is small, of course, this term will be what? Will be big, right? But the residual sum square is also big. All right. For complex model, okay. For complex model, the green term, the denominator term, is small because d is big. Subtract from n. But again, the RSS is also small. So now you have to, that's why you have to find a good balance between the good balance of the ratio RSS versus ratio of RSS to this green term. What would be the good balance? When you increase the model complexity, of course, RSS would be less and less, but is it worth trying to add the model complexity? So again, adjusted R square now is not an increasing function, and you try to pick the model that has maximum adjusted R square. Okay. I have some quick relationships between these scores. It has some more details, but I would like just to conclude it. For the Gaussian noise additive model, when you use AIC, AICc, or BIC, you see that we need to derive the log likelihood function. The model, the data generating process, we often assume in engineering application, it would be like y is some function. This is your assume model as some function of x, right? Predictor plus some noise. Okay. When the noise is corrupted in additive way, we call it noise additive model. All right. If you have assumption that the noise is Gaussian in somehow, typically zero mean, this is called you have Gaussian noise additive model assumption. In this case, we can derive the log likelihood function, and it depends on how you handle the model parameters. In one case, if the noise variant is one of the parameters to be estimated, the log likelihood function can be obtained as the log det of sample covariance matrix of prediction error. If the noise is not a parameter to be estimated, all right, if someone say, okay, I give you the value, my noise variant is this, all right, is this value, I give it to you. So the variance of noise is no longer a parameter, so the way you derive the log likelihood will be slightly changed, and it can be proved that it ends up with what? The residual sum square divided by sigma square, the value that is given. Okay. Now let me recall AIC is negative 2L plus DN, sorry, plus 2D. All right. So when we focus on the second case, when the noise variant is a parameter, okay, AIC, in that case, the negative 2L is RSS divided by sigma square, right, plus 2D. As we see before, the log likelihood function always grows with the sample size, because when you have more measurements, more data, the log likelihood is actually the sum of the log likelihood of yi, right? So typically in so user, some people also consider the AIC in a scaled version, scaled by the number of samples. Okay. Oh, sorry. I think I explained it in a wrong case. Sorry. So the case we're considering is actually no, not the green one. Sorry, is the case of the yellow one, which is when the noise variant is also a parameter. Okay, but we restrict down to the case of the scalar. Okay. When sorry, so this is when the Okay, so now we're going to use the expression of negative 2L from the yellow case, all right? But we consider special case where the scale output is scalar. So negative 2L would be n log of, when this thing becomes a scalar, again, this guy is basically like the mean square error. So this is the log of MSE, all right, plus 2D. Okay, now you divide it by n, okay. We can show that it is approximate, this is going to be approximately the same of the log FPE, okay. Now we take the log, we take the log of FPE, right? This is MSE. So it's going to be log of MSE plus log of this guy. All right. And then this guy can be approximated when d over n is small. All right. So that's the first relationship. All right. AIC scaled is actually approximately as log FPE when d is small. When the model is very sparse, like simple. That's the first relationship. The second relationship is that the green case, which means the noise variant is given, is not a parameter to be estimated. For scalar output, so AIC is negative 2L plus 2D, but when the noise variant is given, it is given by RSS, right, divided by sigma square plus 2D, sorry. And again, if I consider the scaled version of these guys, I divided by n the whole thing. It can be represented, oh, it is actually sigma hat square times CP. All right. In that case, using AIC and CP will pick the same model because they are equivalent in this case. All right, that's all the information. That's all the property, mathematical description, some motivation behind these model selection scores.